What started as a small prototype is now rapidly expanding. This facility, once completed, will be the largest.
This is not a missile base, nor a conventional nuclear plant. This is Stargate, a $500 billion engineering fortress, a figure enough to rebuild 50 Gerald R. Ford-class aircraft carriers. But why are Microsoft and OpenAI funneling their entire might into a single localized point? The answer lies in a staggering figure: 5 gigawatts, an energy consumption equivalent to 5 of the planet's largest nuclear reactors. Here, the boundary between silicon and biological intelligence will be blurred by a system with engineering tolerances measured in microns. Stargate does not operate like any data center you have ever known. It is a gargantuan mechanical organism. The core structure consists of millions of the latest Blackwell GPUs, interconnected by a network of superconducting fiber optics thousands of miles long. The facility is divided into specialized sectors. First is the energy sector, housing Gen 4 small modular reactors, or SMRs. Next is the computation hive, the heart of the system with the highest server rack density in human history. Alongside it is the thermal abyss, an industrial-scale closed-loop liquid heat exchange network. Finally, the Sentinel Shell, a military-grade shield against electromagnetic interference and EMP attacks. Deep inside the computation hive, we face the ultimate engineering challenge: extreme energy density. Each server rack at Stargate emits up to 100 kilowatts of heat, equivalent to the thermal output of an industrial furnace. If the cooling system fails for even 3 seconds, tens of billions of dollars in silicon chips will melt into a useless puddle of slag. To combat this heat, engineers have abandoned traditional air cooling for a revolutionary technique: direct-to-chip liquid cooling. A high-conductivity copper cold plate is pressed directly onto the chip's surface, with dielectric fluid circulating at high pressure. The precision of these connections must be absolute. A single microscopic leak could trigger a catastrophic short circuit. The assembly of Stargate is impossible for human hands. Every component placement is handled by 6-axis robotic arms. In a Class 10 cleanroom environment, these robots operate with a tolerance of less than 0.05 millimeters. Watch as these 2 0-ton modules are positioned. They are guided by real-time laser tracking to compensate for thermal expansion. Every bolt and every cable is assigned a digital twin, monitoring physical stress over its 2 0-year operational life. But the real engineering nightmare isn't just the hardware, it's the power grid required to wake this giant. 5 gigawatts of power. To put that in perspective, it's enough to light up the entire city of San Francisco twice over. The traditional grid cannot handle this. Stargate requires its own dedicated small modular reactors, SMRs. These next-gen nuclear plants are built on-site, providing a constant, carbon-free pulse to the AI's neural network. Notice the specialized substations. They use high-voltage direct current, or HVDC, to minimize transmission loss. This massive energy flow generates a powerful electromagnetic field, necessitating the Sentinel Shell's protection. The shell is a Faraday cage on a gargantuan scale, protecting the delicate logic gates from any external interference. Inside this fortress, we aren't just building a computer, we are engineering the physical substrate of global intelligence. The assembly phase of Stargate marks the transition from heavy civil engineering to sub-micron precision manufacturing. Every single GPU cluster is transported via autonomous maglev sleds to eliminate any vibration that could cause microfractures. The installation floor is a masterpiece of stability, reinforced with massive vibration-dampening pilings driven deep into the bedrock. Engineers utilize augmented reality visors to overlay the one-to-one digital twin of the facility onto the physical hardware. This ensures that miles of liquid piping and thousands of optical cables align with a margin of error thinner than a human hair. Quality control is relentless. Automated X-ray scanners sweep every weld in the cooling system for atomic-level imperfections. A single bubble in a weld could expand under the extreme 5-gigawatt thermal load, leading to a high-pressure rupture. Now observe the neural junctions, custom-built optical switches that bypass traditional bottlenecked networking. These switches use silicon photonics to transmit data at light speed, allowing millions of chips to act as a single, unified brain. The scale of data throughput here is so immense, that it requires its own unique vacuum-sealed conduit system. As we move to the final integration, the facility undergoes a dry run, a massive stress test of the infrastructure. Simulated loads are pumped through the power substations to test the resilience of the small modular reactors. The cooling pumps roar to life, circulating hundreds of thousands of gallons of dielectric fluid per minute. This is the moment of truth. If the harmonics of the pumps resonate with the server racks, the entire system could shake itself apart. But at Stargate, failure is engineered out. Every resonance frequency has been mapped and neutralized by active dampeners. With the physical structure stabilized, we enter the most dangerous phase, the power-up sequence. As the first gigawatt flows into the system, the facility's electromagnetic signature becomes visible on satellite sensors. The ambient temperature in the desert outside drops slightly as the SMRs pull in massive amounts of cooling air. Inside, the dielectric fluid reaches peak velocity, creating a low-frequency hum that can be felt in the marrow of your bones. We are now witnessing the Blackwell awakening, millions of processing cores communicating for the first time. To prevent a grid collapse, the power is channeled through a series of colossal supercapacitor banks. These banks act as a buffer, absorbing the massive surges required during large-scale AI model training cycles. Look closely at the data bus architecture. It utilizes a spine leaf topology upgraded for quantum-ready encryption. This ensures that the intelligence generated here is physically impossible to intercept or decrypt from the outside. But there is a hidden cost. The massive concentration of energy creates a localized heat island effect. To mitigate this, Stargate employs a secondary atmospheric heat rejection system using giant liquid-to-air arrays. These arrays are designed with aerodynamic louvers that adjust to the wind speed of the Nevada desert. Even the air is engineered here. The atmosphere inside the hive is a nitrogen-rich mix to eliminate any risk of oxidation. Engineers must wear specialized oxygen-supplied techwear just to enter the central processing core. In this environment, man is the most fragile element in a temple built for the gods of computation. The scale of Stargate isn't just a feat of construction, it's a masterpiece of logistical coordination. To maintain 99.9999% uptime, the facility utilizes an AI-driven maintenance swarm, hundreds of small robotic drones. These drones traverse the ceiling tracks using thermal sensors to identify failing components before they even overheat. Watch as a drone replaces a faulty transceiver in under 45 seconds, all while the system remains under full load. But even with this automation, the most critical element remains the cold start protocol. In the event of a total grid desynchronization, the SMRs can be isolated into a local island mode within milliseconds. This rapid switching generates massive mechanical stress on the turbine generators, requiring specialized high-tensile alloy shafts. These shafts are forged from a single ingot of nickel-chromium steel, designed to withstand the torque of a sudden load dump. To test this, engineers perform pulse loading, triggering a massive computational spike to see how the cooling reacts. The dielectric fluid pressure surges instantly to 200 pounds per square inches. The roar of the pumps echoes through the 3-mile-long hall. This is a controlled explosion of data and energy, pushing the limits of current materials science. If the vibration dampeners fail now, the harmonic resonance could shatter the porcelain insulators in the power yard. But the data shows a perfect curve. Stargate isn't just surviving, it's thriving under the pressure. The facility is now ready to host the first AGI-level model, requiring more compute than all previous centers combined. As the lights in the control room settle into a steady gold, we realize the world has just entered a new era. But maintaining this digital titan requires a supply chain of unprecedented scale and precision. Every month, thousands of specialized air filters, each capable of trapping particles down to 0.1 microns, are replaced. Even the tiniest speck of dust could settle on a high-voltage trace, creating a conductive bridge and a catastrophic arc. This is why Stargate operates its own dedicated logistics hub, larger than most international airports. Here, automated sorting systems process over 10,000 critical spare parts every single day. The cost of operation is staggering, over $1 billion per month just for electricity and maintenance. To offset this, the facility harvests waste heat to power a secondary desalination plant for the local region. It's a closed-loop ecosystem where engineering efficiency meets environmental necessity. Now, let's look at the global bridge, the dedicated undersea fiber cables connecting Stargate to the rest of the world. These cables are armored with high-tensile aramid fibers to withstand deep-sea pressures and seismic activity. Inside the data landing station, the signal is amplified by Raman amplifiers, boosting data speed to petabits per second. This infrastructure allows Stargate to process global information in real time, effectively becoming a planetary-scale brain. But with such power comes extreme vulnerability. The site is protected by an integrated kinetic defense system. Automated turrets and electronic jamming arrays ensure that no unauthorized drone or signal can approach the perimeter. This is no longer just a private project. It is a critical piece of national infrastructure, a sovereign AI sanctuary. But even a sanctuary needs to be tested against the unthinkable. A full-scale kinetic impact or seismic event, the Sentinel shell isn't just for show. Its foundation is floating on massive hydraulic dampers designed to survive a magnitude 9 earthquake. These dampers utilize a non-Newtonian fluid that hardens instantly upon impact, absorbing gigajoules of kinetic energy. Inside the core, the server racks are suspended by high-tensile carbon fiber tethers, isolated from the building's vibration. Engineers perform a stress drop test, simulating a sudden loss of the primary cooling manifold. Within milliseconds, the emergency cryogenic backup system engages, flooding the pipes with liquid nitrogen. The temperature drops to minus 196 degrees Celsius, freezing the thermal runaway in its tracks. This failsafe is the ultimate insurance policy for a $500 billion asset. As we reach full operational capacity, the Stargate AI begins to optimize the facility's own energy consumption. It reroutes power with nanosecond precision, predicting thermal spikes before they occur based on local weather patterns. The facility has become a self-correcting, living machine, a true symbiosis of heavy engineering and digital mind. Now, the final gate opens. Stargate is no longer just processing data, it is generating new scientific breakthroughs. From room temperature superconductors to carbon capture materials, the solutions are being forged inside these silicon halls. This is why the cost, the energy, and the secrecy were necessary. We were building a ladder to the future. The era of trial and error is over. The era of Stargate has begun. But what does this mean for the average person? Stargate isn't just a server farm. It's an engine of universal discovery. The heat harvested here now powers vertical farms in the surrounding desert, producing tons of crops in a soilless environment. Every kilowatt is recycled, every bit of data repurposed to solve the most pressing challenges of our species. As we look at the shimmering facade of this $500 billion fortress, we see more than just steel and silicon. We see the ultimate proof of human ambition, a monument to our refusal to accept the limits of physics. Inside, the air is still, the nitrogen mix hums, and the golden lights of a billion processors blink in a silent symphony. This facility will be the birthplace of the next industrial revolution, one driven by pure thought and immense power. Security patrols continue their silent rounds, protecting the most valuable secret in the history of technology. The Stargate project has officially transitioned from a construction site to a living, breathing digital sovereign. The USA has secured its place at the forefront of the AI era, anchored by this indestructible fortress of intelligence. As the sun sets over the desert, the lights of Stargate grow brighter, mirroring the stars above. We are no longer just observers of the future. We are the architects of it. Stargate is complete. The mission has only just begun. Thank you for joining us on this deep dive into the most expensive machine ever built. Don't forget to subscribe for more engineering deep dives into the mega projects that are rewriting our world. See you in the future.